Welcome to Tomorrow Unveiled, your direct line to the future of technology, industry, and exploration. You know, if you look at the past week, say September 26th to October 3rd, 2025, it's interesting. You don't really see one single huge headline-grabbing scientific moment.
No, that's exactly right. What we're seeing instead is something quieter, but maybe more profound, foundational stuff, industrial-scale breakthroughs.
Right, the groundwork. And that's really the key observation, isn't it? It feels like the whole global space industry is pivoting.
It absolutely is. The old question for decades was, can we even go there?
Yeah.
You know, to the moon, to Mars.
Sort of feasibility.
But now, the question that's defining everything is, okay, how do we stay there? How do we scale up operations? How do we build a real, lasting economic system out there?
Exactly. And that's our mission today on Tomorrow Unveiled. We want to give you this shortcut, sort of the inside track to understanding this crucial infrastructure that's being laid down, well, right now.
We're definitely entering the age of space industrialization. It's happening.
It really is.
Yeah.
And our dedicated research team, they've sifted through all the noise, and they've identified three big interconnected themes that really confirm this shift. First, we're diving into next-gen secure communications. Think quantum, think optical.
Okay.
Second, there's this intense engineering race going on for cheaper, faster, and importantly, autonomous logistics, propulsion and docking.
And nuts and bolts of moving stuff around. Got it.
And finally, maybe the biggest piece, laying the actual economic foundation for what everyone's calling the cislunar economy. Resource macking, basically.
And that term cislunar, it's so important here. Just so everyone's on the same page, we're talking about that huge volume of space between the Earth and the Moon, right? Including those special spots, the Lagrange points.
Gravitational sweet spots.
And you just can't industrialize that region. I mean, it's impossible if you can't talk securely to your satellites, your landers, whatever.
Right. Or if it costs a fortune to send up every single screw.
Or if you have no clue where the really valuable resources, like water ice, actually are, you need certainty.
And the striking thing this week, according to the research team, is that we saw real progress, like significant steps forward, across all three of those areas, almost in sync.
Simultaneously. Yeah, that's what makes it feel like a genuine turning point.
Okay, let's start with communications then. It's the nervous system, right? The absolute backbone of any space economy.
Absolutely essential.
And for, well, forever really, deep space missions and government operations have been choked by two big problems. The risk of being hacked or listened to, and just not enough bandwidth to send data back.
The twin bottlenecks, security and speed, or lack thereof.
But now it looks like the big global players are finally tackling both of these, and at scale.
Okay, let's talk security first. The big news here comes out of Europe. The European Space Agency, ESA, they just awarded a pretty hefty contract, 50 million.
50 million euros, okay.
Yeah, just for the preliminary design phase, they call it Phase B2, of a mission called SAGA. That stands for Security and Cryptographic Mission.
SAGA, got it. And this is all about quantum key distribution, QKD. Now, quantum can sound intimidating. How do we break QKD down, simply for everyone listening, and why do we need to do it from space?
Right, okay. So QKD is, it's fundamentally different from the encryption we use today. Most current encryption relies on, well, really hard math problems.
Problems that are hard for today's computers.
Exactly. But the worry is that future quantum computers, which are getting closer, will be able to solve those problems, which means sensitive data sent today could be recorded now and just decrypted later. It's a huge vulnerability.
A harvest now, decrypt later threat. That's the one.
QKD just sidesteps the math entirely. It uses the actual laws of quantum physics. It sends cryptographic keys encoded onto single particles of light, photons.
Single photons, wow.
And here's the magic, or rather, the physics. Quantum mechanics, specifically the Heisenberg uncertainty principle, tells us that you literally cannot measure or observe a quantum state without changing it.
Okay.
So if someone tries to eavesdrop, if they try to intercept even one of those photons carrying a piece of the key,
they change it just by looking.
Precisely. The act of intercepting it destroys that part of the key instantly, and crucially, the system immediately alerts the sender and receiver that someone was listening. The link is compromised. Try again.
So it's theoretically immune to eavesdropping because any attempt gives itself away. That's the quantum shield idea.
That's the essence of it. It's physics-based security, not math-based complexity.
But putting this in space, I mean, that sounds incredibly difficult. It's
Yeah.
not just pointing a laser beam, is it?
Yeah.
What are the big challenges ESA needs to crack for Saga?
Oh, the engineering is immense. You mentioned pointing. The accuracy required is just phenomenal. You're trying to send and receive individual photons over thousands of kilometers, often through Earth's atmosphere.
Which is like looking through boiling water sometimes, right? Turbulent.
Exactly. So you need incredibly stable satellite platforms,
Yeah.
plus sophisticated adaptive optics on the ground stations that can actually compensate for that atmospheric wobble in real time. It's a huge challenge.
So why go to all that trouble? Why space?
Because of the reach and the strategic goal behind Saga, putting it in space allows for potentially global key distribution, connecting points that don't have direct line of sight on the ground. But more importantly, it ties into this dual-track strategy our research team flagged.
Ah, yes, the dual track. Explain that.
This Saga mission, it's not a commercial internet project. It's explicitly designed for sovereign use. Governmental data, critical national infrastructure, defense communications, high-level diplomacy, stuff that needs the absolute highest level of security and national control.
So Europe is deliberately creating a separate dedicated QKD network just for official state business, distinct from any commercial QKD efforts that might pop up.
Precisely. They're drawing a very clear line. They recognize that national security demands sovereign control. You don't want your most sensitive military or diplomatic keys potentially transiting through commercial infrastructure that might have different security standards or foreign involvement.
That makes sense. It's a mature approach, really. You have one system built purely for security and state needs, and maybe another more open system for commercial applications later on.
That's what the analysis suggests. This dual-track model, sovereign QKD for the government, commercial QKD for the market, is likely to become the standard globally. You can bet the US and China are watching ESA's Saga development very, very closely.
Okay, so Saga is about securing the data. But what about the other bottleneck? Getting enough data back in the first place, especially from deep space.
Right. The bandwidth problem. Security doesn't help much if you can only trickle back a few kilobytes per second from Mars.
And this week saw a pretty major step in breaking that data bottleneck, using lasers again, but for volume this time.
Yeah, this is really exciting. This is optical communications. ESA managed to establish a stable laser link, like a data pipe made of light, with NASA's Psyche spacecraft.
And Psyche is where exactly?
Way out there. At the time of the test, it was over 186 million miles away. That's 300 million kilometers.
Wow, 300 million kilometers. Just aiming that laser? The precision must be incredible.
It's mind-boggling. You've got the spacecraft moving, Earth moving, the ground station moving, you have light travel time delays. Hitting that target consistently is an astonishing feat of engineering.
And this ESA success builds on NASA's own experiment, right?
Yeah.
The DSOC system on Psyche.
Exactly. NASA's Deep Space Optical Communications, DSOC experiment, is basically paving the way. And the performance numbers they've already demonstrated are game-changing. DSOC has streamed ultra-high-definition video back from deep space.
Actual video, not just telemetry.
Yeah, high-def video. And they hit a peak data rate of 267 megabits per second, MBPs.
Okay, 267 megabps. That's faster than a lot of home internet connections. How does that compare to the usual radio systems used for deep space?
It blows them out of the water. That 267 millibps is at least 10 times higher, maybe much more depending on the specific RF system, than what traditional radio frequency systems can manage over those kinds of distances.
So for decades, missions have been fundamentally limited by radio waves.
Completely data-starved. Think about it. Mission scientists would design these amazing instruments, high-res cameras, ground-penetrating radar, spectrometers that could collect terabytes of data.
But they could only send back a tiny fraction.
Just a trickle. Maybe a few key images, some compressed data, sent back painfully slowly over months, even years. You collect vastly more than you can ever transmit.
So optical comms, this laser communication.
Right.
This unlocks what the research team called the high-definition solar system. That's a great phrase.
It really captures the shift. It means scientists can stop designing instruments around the communication bottleneck.
And start designing them to capture everything.
Pretty much. Imagine planning for near real-time video monitoring of volcanic eruptions on Jupiter's moon Io, or getting detailed, high-resolution scans of Martian subsurface ice deposits back in days, not years.
Or watching Martian dust storms evolve almost as they happen.
Exactly. You can plan for instruments that generate terabytes because you know you can actually get that data back relatively quickly. It compresses the timeline for scientific discovery dramatically. It changes deep space exploration from sending postcards to something closer to having a live, high-def remote presence. It's a paradigm shift.
Okay, so secure high bandwidth comms, that's step one checked off.
Mm-hmm.
Step two is fixing how we actually move things around in space and get them back.
The physical transit layer, yeah, absolutely critical.
And the next set of breakthroughs our team highlighted focuses squarely on making space travel and orbital logistics much cheaper, much faster, and much more routine, which, you absolutely need if you're talking about industrial scale.
And the most potentially disruptive development here, certainly in terms of speed and efficiency, comes from GE Aerospace. They successfully tested 2 engines based on rotating detonation combustion, or RDC.
RDC. Okay, that sounds intense. Rotating detonation. Are we basically talking about controlled explosions instead of controlled burning?
That's a pretty good way to think about it, yeah. Almost all current jet engines and rocket engines use what's called deflagration. It's a subsonic burn, like a flame front moving through the fuel-air mixture relatively slowly.
Okay, standard burning.
RDC is totally different. It uses detonation, a supersonic explosion wave that continuously travels around inside a ring-shaped and annular combustion chamber.
A continuous, stable, supersonic explosion going around in a circle. How do you even control that?
That's the incredibly hard part. But if you can sustain it, that detonation wave releases energy much, much faster and more completely from the fuel than a slow burn does.
So more efficient, more power from less fuel.
Exactly. And because it's so much more intense, you can potentially get the same amount of thrust from a much smaller, lighter engine. That's the holy grail in aerospace, reducing size and weight.
And GE's test, what did they achieve?
The big number our research flagged was a 3x increase in the engine's airflow handling compared to their previous RDC demonstrators.
3 times the airflow. Why is that specific metric so important?
In engine development, airflow is king. More airflow, generally speaking, means more potential thrust, better efficiency at high speeds. A 3x improvement is a huge leap. It directly points to the potential for RDC-powered vehicles, missiles, hypersonic aircraft, maybe even upper stages for rockets to be dramatically smaller, or fly much farther, or carry way more payload.
This sounds almost revolutionary. If it's so much better, why aren't all engines RDC already? What are the big hurdles?
Well, controlling that continuous supersonic detonation is incredibly difficult. That's the main challenge. You have to keep it stable, prevent it from fizzling out or becoming just inefficient burning. It demands unbelievably precise fuel injection and mixing.
And the heat and pressure must be insane.
Off the charts. The material science needed just to contain that environment, to stop the engine from literally tearing itself apart, is extreme. You're pushing metals and ceramics right to their absolute limits.
So the fact GE got this 3x airflow number suggests they're making real progress on those stability and materials problems.
That's the implication. And the research team calls this a disruptive forcing function. Because if GE or anyone else masters RDC, it forces everyone else, especially global competitors, still relying on older scramjet designs for high-speed flight, to either catch up fast with their own RDC work or risk being left behind strategically. It changes the game.
Okay, shifting from high-speed engines to maybe less glamorous but equally vital. Orbital logistics, just moving cargo around. Northrop Grumman, working with Voyager Technologies and Starlab Space, had a big success.
Yeah, they successfully demonstrated autonomous rendezvous, proximity operations, and docking RPOD using a simulated Cygnus cargo ship with the future Starlab commercial space station.
Autonomous docking. So the computers handle the whole approach and connection.
That's the idea. And while it might not sound as exciting as detonation engines, this is absolutely crucial for making commercial space stations actually work financially.
How so? What's the big cost driver it addresses?
It's a direct attack on operational costs, the OPEX. Think about the International Space Station right now. When a cargo ship like Cygnus or Dragon arrives...
Astronauts spend hours watching it, right? Ready to take over.
Exactly. Highly trained, incredibly valuable astronauts spend precious time just monitoring the approach, often with huge teams on the ground backing them up. That crew time is by far the most expensive resource in orbit.
So autonomous RPOD means the spacecraft basically docks itself, like an autonomous valet parking a car.
That's a great analogy. It significantly reduces, or maybe even eliminates, the need for that intensive human oversight for routine cargo deliveries.
Freeing up the astronauts to do the actual science or manufacturing the station was built for.
Precisely. It lets them focus on the high-value tasks. Now, there's always a risk trade-off, right? You're shifting reliance from potential human error in a stressful situation to software reliability,
Making sure the software is absolutely bulletproof.
which is why these demonstrations focus so heavily on redundancy and fail-safes. But the bottom line, according to all the analysis, is clear. Without cheap, reliable, autonomous logistics, the business models for all these planned commercial EO stations just don't close. The OpEx is too high. This demo proves a key technology needed to make them viable.
And still on logistics, but coming back down to Earth. Literally. There's a startup, Inversion Space, that unveiled a vehicle called ARC.
Ah, yes, ARC. This one's fascinating. It's designed to be a fully reusable reentry vehicle. Think of it like a small, unmanned spaceplane, but a lifting body design.
And its purpose.
Rapid global delivery from orbit. The headline capability is delivering about 225 kilograms, roughly 500 pounds of cargo anywhere on Earth within an hour after deorbiting.
An hour. From orbit to anywhere on the ground. That's incredible speed.
It's true point-to-point orbital speed logistics. They're designing it to survive re-entry from speeds over Mach 20.
Mach 20. The heat shielding alone must be state-of-the-art.
Absolutely. And it's a lifting body, meaning its shape generates aerodynamic lift, allowing it to maneuver during re-entry, not just fall like a capsule. This helps with managing heat and, crucially, allows for precision landing.
How precise?
They're targeting landing within 15 meters of the designated spot, and they plan to use non-toxic propellants for the final touchdown burns, which simplifies ground operations.
Okay, so if they pull this off, the first orbital flight is planned for 2026, the research said.
Correct.
If that works, what are the applications? Defense seems obvious.
Defense, definitely.
Yeah.
Imagine delivering critical repair parts, specialized sensors, or emergency supplies to troops anywhere in the world almost instantly. But also think about humanitarian aid getting vital medicines or communication gear to a disaster zone immediately.
Or even high-value commercial logistics down the line.
Potentially. It could lead to orbital warehouses, preposition depots holding these ARC vehicles loaded with different types of cargo, ready for dispatch on an hour's notice. It fundamentally changes the concept of a global supply chain.
It really does. That kind of capability just shrinks the planet. Okay, this perfectly illustrates the sheer engineering ambition we're tracking here on Tomorrow Unveiled. Before we move on to the economics, the actual why behind building all this infrastructure, let's just pause for a moment. If you're finding this insightful, maybe learning something new, please take a second to like this video if you're on YouTube, subscribe to Tomorrow Unveiled, and maybe even hit that new hype button. It really helps us reach more viewers. And definitely turn on notifications so you don't miss what's coming next.
And if you're listening on a podcast service, maybe Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and maybe a quick review for Tomorrow Unveiled. Honestly, it makes a huge difference in helping new listeners discover the analysis our dedicated research team puts together each week. Your support really does fuel this.
All right, welcome back to Tomorrow Unveiled. We've talked about secure, high-speed communication. We've covered cheaper, faster, autonomous transit. Now we need to tackle that third pillar, the one that really underpins everything, establishing the economic basis for doing business beyond Earth.
Yeah, moving from just exploring the moon to actually exploiting its resources, it's a huge shift in mindset.
And the biggest news driving this shift this week seems to be Project Oasis. This is Blue Origin partnering up with Luxembourg.
That's right, the Grand Duchy of Luxembourg. And that partnership itself is really telling.
How so? Luxembourg isn't exactly known for launching rockets.
No, but it is known internationally for its sophisticated financial sector and, crucially, for having a very deliberate, forward-thinking government policy aimed at attracting and enabling space resource companies. Their involvement signals that Project Oasis isn't just science.
It's finance. It's about mapping potential wealth.
It's fundamentally about de-risking the economics. Project Oasis is planned as a multi-phase campaign to systematically map lunar resources. The first mission, Oasis 1, will use a small satellite flying in a very low lunar orbit.
And what's it looking for specifically?
The key targets are water ice, using neutron spectroscopy to map concentrations down to about a meter below the surface. Also, metallic deposits, using magnetometers. And they'll use multispectral imaging to look for other valuable materials, maybe rare earths, and even helium-3.
Helium-3, the potential fusion fuel. Okay, so water, metals, fuel. Basically the essential ingredients you'd need to build a self-sufficient outpost or industrial base on the moon, right?
Exactly. Water for life support, split into hydrogen and oxygen for rocket fuel, metals for construction, fuel for power and propulsion. But the mapping itself is the crucial first step. Why now?
Why is just knowing where it might be so critical?
Because right now, the biggest barrier stopping serious investment in, say, a lunar water extraction plant or a metals refinery isn't the technology itself. We largely know how to do that stuff. The barrier is the financial risk stemming from resource uncertainty.
Meaning, nobody wants to spend billions building a factory if they aren't sure there's enough easily accessible raw material nearby to make it pay off.
Precisely. Would you build a giant gold mine based on a vague map that just says, maybe gold somewhere in this mountain range? No way. You need detailed geological surveys confirming the grade, the depth, the extent of the ore body.
Okay, so Project Oasis aims to create the lunar equivalent of those detailed mining surveys.
So that's the core idea. The research team calls it producing investment-grade resource maps, data that's reliable and detailed enough to satisfy investors, bankers, insurers, data you can build a solid business case on.
That's a fascinating concept, investment-grade lunar data. It's not just science data, it's a financial product.
It really is, and this is the business model innovation. By creating this proprietary high-fidelity data set, Blue Origin does a few things. They dramatically de-risk their own future lunar ventures, obviously.
Like their Blue Alchemist program.
Exactly, which aims to turn lunar regolith, the soil, into things like solar cells and wires. Oasis tells them where the best feedstock is. But beyond that, this data itself becomes incredibly valuable.
How so? They could sell the maps.
They could sell the data, they could lease out prospecting or extraction rights to specific resource-rich areas they've mapped, they could trade claims like terrestrial mining companies do, or they could use these certified resource assets on their books to secure much larger amounts of financing for their own projects. It basically creates a new market, resource prospecting as a service.
But hold on, if Blue Origin generates all this key data first, doesn't that give them a massive, potentially monopolistic advantage, controlling the entry ticket to the lunar economy?
That's a really important question, and yes, initially having that detailed proprietary map gives them a huge first-mover advantage and significant leverage, no doubt about it.
So how does competition emerge?
Well, a couple of things. First, actually extracting and using these resources is still incredibly complex and expensive. Blue Origin will likely need partners, customers, licensees eventually. Second, and perhaps more importantly, the moment any company, even Blue Origin, successfully demonstrates that lunar resources are economically viable, that the uncertainty barrier is broken, it fundamentally lowers the risk profile for everyone else.
Oh, so their success actually encourages others to jump in.
It makes it much easier for competitors, maybe national space agencies or other commercial players, to get funding for their own mapping missions to verify or challenge Blue Origin's findings and find their own claims. Success breeds competition, especially when potentially trillions of dollars in resources are at stake. A long-term data monopoly is unlikely once the gold rush truly starts.
And internally for Blue Origin, this Oasis data feeds that flywheel effect the research mentioned.
Absolutely. Oasis finds the water ice. Blue Alchemist develops the tech to use it. Using that water for fuel on the moon, in situ resource utilization, or ISRU, could, according to their projections and analysis, cut the cost of missions going further out, say to Mars, by up to 90%.
Because you don't have to launch all that fuel from Earth's deep gravity well.
Exactly. Cheaper deep space missions create more demand for lunar infrastructure, which needs more resources found by Oasis, which improves the tech from Blue Alchemist. The flywheel spins faster.
Okay, speaking of the cost of getting things to space, which underpins all of this, we need to look at the launch providers.
Yeah.
Rocket Lab had a significant win this week.
Yeah, they secured a second big contract with a company called Synspective, a satellite imaging company. This adds 10 more dedicated launches using Rocket Lab's smaller Electron rocket.
10 more, on top of previous ones.
Right. It brings Synspective's total commitment to 21 Electron missions. That's the single largest order for Electron Rocket Lab has ever received.
21 launches. That sounds like a really solid baseline of business.
It's strategically crucial. Our analysis identifies this as a perfect example of Rocket Lab executing what we call a barbell strategy to ensure their financial health and fund future growth.
Okay, explain the barbell strategy. What are the two ends?
So on one end of the barbell, you have the Electron rocket. It's proven, reliable, flying frequently. It serves a very specific, high-margin niche market, dedicated launches for small satellites.
Companies like Synspective who want their own ride on their own schedule.
Exactly. They're willing to pay a premium for that schedule certainty and the precise orbital insertion Electron provides, rather than, say, waiting months for a spot on a larger rocket's rideshare mission where they have less control. This creates a steady stream of reliable, profitable revenue for Rocket Lab, consistent cash flow.
Okay, that's the stable, profitable end of the barbell. What's on the other end?
The other end is the high-risk, potentially high-reward development project. Their much larger, next-generation reusable rocket called Neutron.
Neutron is aimed at the bigger satellite market. Constellations, national security.
Precisely. It's designed to compete directly with larger vehicles from SpaceX and others in those much bigger, more lucrative markets. But developing a large reusable rocket from scratch takes an enormous amount of capital, years of work, and carries significant technical risk. It's a big bet.
Ah, I see. So the reliable profits from the Electron launches, like these 21 missions for Synspective, provide the stable financial foundation and the actual cash needed to fund the expensive, risky development of Neutron.
That's the strategy in a nutshell. Use the success and profitability of your established niche product, Electron, to de-risk and finance the development of your potentially game-changing future product, Neutron. It's a smart way to manage growth and innovation in a capital-intensive industry like launch.
All right, so we've got the tech advancing, the economics starting to pencil out. But as space gets busier, especially near Earth, the complexities just multiply. We need rules, we need safety protocols.
Yeah, the rules of the road are lagging way behind the traffic density. That's a growing concern.
Which makes this next item particularly interesting. It seems like a moment where practical necessity kind of cut through political red tape.
Definitely. This involved direct communication between operators at NASA and the China National Space Agency, CNSA.
About a potential collision.
Exactly. They had 2 satellites in low Earth orbit on paths that looked like they might pose a collision risk, and CNSA initiated direct operator-to-operator contact, reportedly just via email with NASA, to coordinate avoidance maneuvers.
And our research team confirmed this was the first time this kind of direct operational contact happened between the two agencies for a specific collision warning.
That's what the reporting indicates, yes. First time. And what makes it so significant is that it happened despite major political hurdles.
You mean the Wolf Amendment?
Specifically, yes. For listeners who might not track space policy, the Wolf Amendment is U.S. legislation, passed over a decade ago, that puts very strict limits on bilateral cooperation and coordination between NASA and Chinese state-run space entities, primarily due to national security and technology transfer concerns. It makes formal official communication extremely difficult.
So, faced with 2 satellites potentially smashing into each other and creating thousands of pieces of debris, the actual operators on the ground just found a way to talk to each other directly, sidestepping the politics.
It seems so. Pragmatism born of necessity. Because the alternative, a collision, is bad for everyone, regardless of nationality. The communication itself is apparently very simple, very technical.
What did it say?
Something along the lines of, we see a potential conjunction, we plan to maneuver, we recommend you hold your current trajectory. Just the basic operational facts needed to ensure safety.
Wow. So it's not a treaty, it's not a formal agreement.
Yeah.
It's more like the beginning of operational common sense.
You could call it the birth of operational trust, maybe. It's an informal protocol emerging because the physics of orbital mechanics and the danger of debris demand it. When things are closing at, 17,000 miles per hour, the bureaucratic hurdles have to take a back seat to basic safety.
It's a fragile precedent, though, isn't it? Just an email exchange.
Extremely fragile, but absolutely crucial. LEO is getting dangerously crowded, and there's still no effective international space traffic management system. These kinds of ad hoc, professional, transparent interactions, if they become consistent, are essential. They build the foundation of predictable behavior needed to operate safely as space gets even busier and more commercialized.
And finally, staying safe and functional isn't just about avoiding collisions. It's also about keeping the humans and the sensitive equipment working properly on those long journeys, like to the moon or Mars.
Right. Long-duration spaceflight poses huge challenges to both biology and technology.
Our sources highlighted a couple of interesting developments here. First, on the human side, something called HS Mart.
Yes, this comes from NASA's TRISH, the Translational Research Institute for Space Health. HS Mart is a platform using artificial intelligence combined with eye-tracking technology.
Eye tracking to monitor astronauts.
Exactly. The idea is to monitor an astronaut's cognitive state, things like mental workload, fatigue, stress in real time, just by analyzing subtle patterns in their eye movements. Blink rate, pupil dilation, how their gaze moves.
So it's trying to detect if an astronaut is getting overloaded or dangerously tired, even if they don't realize it themselves.
Precisely. It moves beyond relying just on astronauts self-reporting how they feel. Think about a crew on a 9-month trip to Mars. Cumulative fatigue is a serious risk.
Especially if something unexpected happens and they need to react quickly and accurately.
Right. HS Mart aims to use these involuntary eye movement patterns, which are linked to the autonomic nervous system, to predict degradation in cognitive performance before a critical error might occur. It could allow mission control or even the spacecraft's own systems to suggest rest periods or reassign tasks proactively. It's about maintaining peak performance and safety when help is millions of miles away.
That's fascinating, like a cognitive early warning system.
Roger.
And on the hardware side, keeping the electronics alive.
Yeah, the other key advance flagged was from a company called Cosmic Shielding Corporation. They got Pentagon funding specifically, TACFI funding for their radiation shielding technology, which they call Plasteal.
Plasteal. Sounds like something out of science fiction. What does it do?
It tackles the relentless problem of radiation in space. Cosmic rays, solar particles, they bombard spacecraft constantly, and they are particularly damaging to sensitive electronics. They cause glitches, data corruption, and shorten the lifespan of components dramatically.
Especially the advanced commercial chips everyone wants to use because they're faster and cheaper, right?
Yeah.
They aren't usually built for space radiation.
Exactly. Traditional shielding, like using thick layers of aluminum, adds a lot of weight and bulk, which is always a penalty on a spacecraft. Plasteal is designed to be a high-performance, potentially lighter shielding material.
And how effective is it?
The key result highlighted was that it demonstrated an 8-fold increase in the operational lifetime of electronics exposed to radiation compared to unshielded components.
8 times longer life. That's huge.
It's transformative. It could allow missions, both commercial and government, to confidently use more powerful, cutting-edge commercial processors and sensors, even in harsh radiation environments, like deep space or certain Earth orbits, without sacrificing reliability. It helps bridge that gap between terrestrial tech and space-hardened requirements.
Wow. Okay, when you pull all these threads together from the past week, the secure comms, the faster engines, the autonomous docking, the resource mapping, the safety protocols, the health tech, it really paints a picture, doesn't it?
It absolutely does. Stepping back, you see these aren't just random, isolated advancements. The research team's synthesis is spot on. They are interlocking pieces. They're feeding each other, creating this synchronized flywheel effect that's genuinely accelerating space industrialization.
Let's quickly recap that flywheel connection.
Okay, so Project Oasis starts mapping lunar resources. That creates the demand signal, the economic pull, by proving there's actual wealth there.
Right. Then optical communications fix the data bottleneck so you can actually do that sophisticated mapping effectively and monitor future operations.
Then autonomous RPOD, like the Starlab demo, starts to fix the logistics cost, making it cheaper to build and resupply the lunar infrastructure needed to get those resources.
And engines like RDC potentially fix the transit speed and cost, making it faster and more economical to move people and high-value hardware between Earth and the Moon.
And finally, those fragile deconfliction efforts, like the NASA CNSA email, start to address the traffic safety problem you absolutely need to solve if you're going to have dozens or hundreds of missions operating in cislunar space simultaneously. It all connects.
It really does. It confirms that pivot we talked about at the start, from pure exploration to building an actual economic domain.
Right.
So looking ahead now, based on everything we've discussed here on Tomorrow Unveiled, what should we be watching for next? What are the signposts?
Well, a few things seem likely based on this trajectory. First, regarding the moon, watch for other big aerospace companies or maybe even national space agencies to announce their own lunar resource mapping missions. Blue Origin fired the starting gun with Oasis, aiming for investment-grade data. Competitors won't want to let them own that foundational market for long.
Okay, competition in lunar prospecting. What else?
Second, back to secure comms. Expect to see state-sponsored players, almost certainly the US and China, formally announce their own sovereign QKD satellite programs. Europe's Saga is leading the way, but this dual-track security approach, separate systems for government and commercial, will likely become the global norm.
So confirmation of that sovereign versus commercial split worldwide. Makes sense.
And third, building on that NASA CNSA email exchange, look for subtle moves. Maybe not public treaties, but perhaps towards a more established, maybe still informal hotline or regular channel for operational space safety communication between major players. That pragmatic need for deconfliction isn't going away, it's only going to grow. Predictable behavior is key.
Fascinating. So much happening just below the surface.
Definitely. And we genuinely love hearing what you think about all this. Whether you're watching on YouTube or listening on your favorite podcast app, please drop a comment. Let us know your take on this new era of space industrialization. What excites you? What worries you?
Yeah, absolutely. The shift we've tracked this week feels pretty undeniable. Space is rapidly becoming less of a final frontier for explorers and more of an economic frontier ripe for development, which leads to our final provocative thought for you to mull over. Given these breakthroughs, especially in lower-cost launch, maybe RDC propulsion down the line, and autonomous operations, what terrestrial industry do you think will be the first to seriously consider moving a core part of its operations? Maybe primary manufacturing, maybe massive data centers off-world, once the infrastructure is there and the economics become truly compelling.
And following on that, what does the supply chain even look like when it starts with raw materials mined and processed on the moon, before maybe being shipped back to Earth or used in deep space? It boggles the mind a bit.
It really does. Food for thought.
Well, thanks for joining us for this deep dive on Tomorrow Unveiled.
We appreciate you tuning in. We'll see you next time.